Good morning. Thanks for coming, and thanks to all of you. I'm going to talk a bit about this approach we recently developed, and I invite you guys. It's pretty simple, straightforward to try it out with your longitudinal data sets. So, as a motivation, when we talk about brain structure correlation with behavior, for example, here, cortical thickness regress against G, the general factor of intelligence. You see all these highlighted regions. But what's more interesting is how is the correlation between a seed region here with another target region. So how are these two regions of the brain, are there coordinated changes, and specifically during development? And what would that mean for studies in development? Turns out, structural covariance networks where you study this correlation of brain structure, either cortical thickness, gray matter volume, surface area, be it anything, between any seed and a target across a population, it could be used as a framework to study coordination in brain structure. For example, the first of these studies was led by Jason Lurs in 2006, where he put a seed in Broca's region, and he observed that it nicely mimics the probability map of Broca's connections with Wernicke's areas. This led to a field where an elegant example by Zielinski, where he looked at structural covariance networks across development, 4 age groups: early childhood, late childhood, early adolescence, late adolescence, and seeded at sensory motor areas, language areas, executive controls, and he showed these dramatic changes in the structural covariance networks during these 4 developmental groups. In another example, compared to controls in AST, you see a remarkable decrease in the structural covariance networks, which is quite profound in itself. Now, this was an example of a seed and a target. You could do this for the whole brain, where you parcellate the brain, for example, in here, based on the AL parcellation, 78 cortical regions, and between any 2 pair of regions, you could get the correlation of the brain structure, and that correlation value leads to a correlation matrix, structural covariance matrix, and this in itself has led to a field where it has been used to investigate brain development in disease with relation to cognition. There are some nice reviews by Alexander Bloch and Alan Evans. And it's been shown that structural covariance networks may partly reflect structural connectivity as inferred with white matter tracks, as well as functional connectivity using fMRI. Now, all that is good, but the main limitation of that is you need a population, you need a group to get the structural covariance. So it is not possible to look at individual variability using that approach. So we tried out this method where we said, instead of looking at structural covariance or the correlation between any 2 regions, how about we look at any 2 regions using longitudinal data points? So for example, in the lower panel, what I'm showing is a toy example of 2 brain regions with 3 time points. And we are interested in looking at how similar these cortical thickness changes is during development. The main motivation behind this is structural covariance network. The hypothesis is that during development, regions of the brain, for example, bilateral homologous regions, they are driven by the same growth factors. So it turns out that they co-vary across the population. With that same logic, we could speculate that during development, it's possible that regions of the brain could also co-vary. Either they grow together or they shrink together. That's the hypothesis. So this is the schematic. So what we have done is, and it's one of the approaches, you could come up with other approaches where we are trying to see how similar the trajectories are between any two ROIs using the 3 time points. So what we have done here is, between time points T1 and T2, we look at the angle of separation, how small or how big the angle of separation is, and you do it similarly for time point 2 and 3, and possibly for 3, 4, or 4, 5. And what, in the end, we ended up using cosine of the theta, because cosine of the theta is more stable and the values range from 0 to 1. But like I said, you could come up with other measures which could capture this similarity index for any two trajectories. So in the end, we define this maturational coupling index between any two pair of regions, and you could do this for the rest of the brain regions. The first thing we wanted to see was, how does it match with the population-based structural covariance matrix? So on the left is the population-based structural covariance matrix, and on the right is the average of the maturational coupling for all the subjects, in this case 141 subjects. Qualitatively, you could see the upper quadrant, that's the left hemisphere, and the lower quadrant is the right hemisphere, and in between are the bilateral regions. You could see a similarity which is quantified by the comparison of the correlation coefficients. So you see around 0.8 correlation between the two matrices. And for better visualization, we showed it with binary, where we were interested in looking at only the 13 topmost connections or topmost edges. So this is interesting and promising. Now, to go into more validation and to also show the scope of the approach, we look at the effect of gender. So what I'm showing here is, on the brain map, females minus males, the difference in maturational coupling index of homotopic regions. So wherever the significant regions are, it shows that in females as compared to males, there are stronger maturational coupling in all these regions, but not the other way around. We don't see this in males. And we think that this is consistent with the idea of more bilateral connections in females as compared to more lateralized connections in males. So you have more stronger, significant maturational coupling of the homotopic regions in females as compared to males. And then another application and scope of the approach was shown by looking at the maturational coupling which sit at one of the default mode regions, in this case the right medial posterior cortex, and it nicely mimics the default mode pattern. What is more interesting is now that since we have a subject-based metric, we can now look at the individual variability with A's. So on the B, we have the same maturation coupling within the default mode, because it's seated at right medial posterior cortex. But now we are looking at the effect of A's, and it turns out the medial PFC is the strongest, is the region with the strongest association, meaning during development, medial PFC and the seat of the default mode, medial posterior cortex, they have a stronger maturational coupling, and they increase with A's. And this is also consistent with findings from DTI, fMRI, where we see increased connectivity, structural as well as functional, during development within the default mode regions. Now, how about the applications of this approach? This is work led by very fantastic Karolina Mentowski, a PhD student in the lab. What she has done is, she used quantitative MRI, so not cortical thickness, because quantitative MRI is microstructural indicator of myelin content. And she looked at hippocampal, 18 regions of hippocampus, and the DKT parcellation, so 62 ROIs, and she used the maturational coupling in approach. And she took it further. She used idea from graph theory, in particular participation coefficient, which gives an index of how heaviness of your nodes. So for example, what she's interested in this work is the green is the hippocampal module with all the 18 nodes, and she's interested in using these maturational coupling matrices. Which of these nodes, which of these hippocampal regions come out as the node with the most central connections to the rest of the brain? So this is the maturational coupling matrix with the highlighted square from the hippocampal regions, and she used it for first episode psychosis subjects versus controls. And in all these blue highlighted regions, the maturational coupling index from hippocampus to and the rest of the brain, it was lower for the subjects with first episode psychosis, and the yellow ones are the ones where it was higher. Now, interestingly, when you look at the participation coefficient for the whole brain, it turns out that subjects with first episode psychosis, it's significantly lower. And if we look post hoc, it turns out that the regions of hippocampus, they come out as this significantly hubs with chains between the two groups. So bilateral, the green regions are highlighted. And most importantly, in the last, among these hippocampal regions, the participation coefficient values, they related with negative symptoms and verbal memory of the subjects with first episode psychosis. So this was just one application of the approach. What we have shown is that it is possible that we could use longitudinal MRI to measure individual level changes in maturational coupling, and that may provide a mechanistic viewpoint of population-based structural covariance networks. Second, it allows for individual variability in brain and cognition. And future projects which we are currently working are how does this subject-based maturational coupling based on cortical thickness or brain structure converse or diverse from white matter connectivity matrices or functional connectivity matrices. But the take-home message is that using longitudinal MRI, one could come up with simple ideas where you could look at similarity of trajectories as highlighted here, and you could use it at the level of individual subjects. Thank you.